This video is about arc length and rotational velocity. We're going to cover quite a few word problems. First, let's establish the relationship between arc length and angles and the radius of a circle. What we have here is an illustration of some rotation that has occurred. This segment that goes from the origin outward into quadrant 1 is the terminal side, where we imagine that this segment begins going completely horizontally on the x-axis and has undergone some rotation along the circle. So here's our radius r. It goes only to the edge of the circle. This line goes a little bit past. It has gone through some rotation. We'll use Greek letter theta to represent the angle or radian measure of this rotation. And there is a corresponding arc length s, which is this piece in between our initial point at 0 degrees and our ending point after this line has gone through a rotation theta. If you have recently been working with the unit circle, then you would have seen problems where the angle and this piece of the circle were the same, but that relationship is only true on a unit circle when the radius equals 1. For circles of varying sizes, this relationship is described by arc length is radius times the angle measure. So this is the first important formula to memorize. S equals r theta. It is the basic relationship between radius of the circle, the angle of rotation, and the corresponding arc length. One detail that's very important to point out is that theta in this formula is in radians. It is by default in units of radians. So we would not want to find theta using this equation and have an answer in degrees. If we wanted an answer in degrees, we would actually have to convert our answer from radians into degrees, and we'll see some examples of that shortly. Now let's talk about the quantities involved when points rotate along the edge of a circle. Here are 2 points rotating along circles. The inner purple circle has a radius of 2.5, and this outer circle radius 5. Let's first talk about which of these points is moving faster. And you could think of this in 2 different ways. For one, they're each taking the same amount of time to go all the way around the circle. They're both moving at about 11 rotations per minute. About 5.5 seconds for each of these circles to make one full rotation, but it's one rotation in equal amounts of time. So in that sense, they're moving at the same speed. But now think about speed in terms of distance covered per time. We know this circle with radius 5 has a greater circumference. Its circumference is twice as long as the circumference of this inner circle with radius 2.5. So the outer circle is actually covering more ground in the same amount of time. So in that regard, it is moving faster. So we're making a distinction between 2 different types of speed. A rotational speed, which is how far around the circle is it going per time, or what angle is it traveling per time, and linear speed, which is more like the speed that we're used to dealing with, like distance equals rate times time, rate is distance divided by time, that kind of speed where we're thinking about the actual distance along the edge of the circle that the point is traveling. And that's where we're going to work in the other values, s for arc length, and we'll keep using theta for angle, and the radius r is going to play a role as well. Here's where the points end up after moving for 1 second. These points have different radii. Definitely one has radius 2.5, the other radius 5, and we're talking about the circles along which they're moving. But they have the same angle. They've moved for the same number of radians or degrees. But we can definitely see that their arc lengths are different. The relationship that we want to use when we refer to the fact that they've moved the same angle per time, that's our angular velocity or rotational velocity or rotational speed. Basically any combination of rotational or angular and velocity or speed. And that is describing the angle that we've traveled per time. So it is a speed in terms of a kind of distance per time, but it's not distance in terms of the arc length, the path that it's traveling. It is in terms of just the angle of rotation it has made. So angular velocity will tell us that these two have the same value for angular velocity. They're moving the same angle per time. This becomes our second important formula to memorize. Omega equals theta over t. It looks like a lowercase w, but it's a lowercase omega, Greek letter omega, and it's measuring the angle that's traveled per time.